So, hold on. Okay. So here's Josh and I's presentation for Busch Gardens. Um, right here we have the side view of our coaster, which is Apollo's Chariot. And this is the first hill and bottom of the first hill. First hill is also the tallest hill, and the greatest acceleration will be on this hill. The fastest speed will be at the bottom of the hill. And yeah. So here's our labeled graph of the Apollo's Chariot, and so here's the first hill, second hill. Helix section is where we kind of have our loops and such. And then right here is where that's the normal force of just staying still, and then here's where we're going up the hill, so we have slightly less than normal force. We're being assisted by the chain hill. So this is some of our info about the coaster found online. The riders ascend 170 feet on the chain lift hill before dropping 210 feet at an angle of 65 degrees. And due to this, we have our 65-degree angle drop, and using trigonometry, we found the hill to be approximately 70.6 meters long. And kinematics equations, we figured at the bottom of the first hill, we should be traveling about 24.18 meters per second, which is equivalent to 54 miles per hour, which sounds about right.
The energy went from KE to KE plus UG when it got to the top, and then once it started going down to the bottom of the hill again, it went to KE, and it lost UG to conserve energy in this situation. We used the Apollo's Chariot. We felt the most force when we were going down the first hill, because that's when we experienced the greatest acceleration as well. We experienced the least amount of force when we were going up the chains for the first hill, because it was constant acceleration and no force was acting upon us, besides Fn, which was pointing up, and then also force of gravity, which was pointing down. The safety bars are put in place so that the riders don't fly out of their seat, because the inertia would have the rider go flying upwards when they go up a hill or something like that. So they helps keep the riders in their seats when going over a hill. From a rider perspective, rides are pretty much fun when they're like a bunch of drops and like loop-de-loops and twists like that. That's what really makes the rides fun. For a physics point of view, what really makes the ride fun is the acceleration that the person feels when they're accelerating down a hill, or when there's centripetal force and they're accelerating inside like a circle or like some kind of like a twist. That's like what the physics is behind when we say a part of the ride is fun.
Still, we can analyze some of these. So you can tell where the collisions happen because of the change in acceleration in the x, y, and z directions. Probably less for y than for x and z though. But so right here, the z acceleration changed a lot, which means the rider was likely hit from the side as opposed to front, or from the front or from the back. Same here, z is much greater than x. But it's false. It's actually not true here. The rider was likely hit from head-on or from behind. The acceleration is more for the x than for the z. And so, in terms of going fastest or slowest, I'm not sure if that applies here. I guess the acceleration is pretty great here, so we're probably traveling fast, like right around here. Largest force, obviously, right here, huge collision, large acceleration. Also, large forces here, here, and here. Um, so, in terms of physics concepts, we have conservation of momentum, not energy, but conservation of momentum due to the collision. Likely when two of the bumper cars collided, and because they have similar masses, the combined velocity after the collision is the same as the combined velocity prior to the collision.